Hello everyone, welcome back. Today we're going to cover our last lesson in chapter 11, 11.7, and it's on geometric probability. So here's kind of a fun little problem to introduce probability. If you and your friends share this pizza, what is the probability that you will get the slice with the ghost chili? So it says play pizza roulette. Ask nicely and we'll put the hottest chili known to mankind on one slice of your pizza. It doesn't cost, but someone pays. Well, you guys are probably pretty familiar with probability in general. So the probability that you would actually get the slice of pizza with the ghost pepper is 1 chance out of 8 slices. And you can give your probability answer simply as a fraction. There's a 1 in 8 chance or 1/8 chance. Or you could give your probability as a decimal, 0.125. Or you could give it as a percent, which would be 12.5%. So you have a 12.5% chance of getting the slice of pizza with the ghost chili. So probabilities are between 0 and 1. So sometimes when we talk about probability, we're really talking about the likelihood that an event will happen. And we're always talking about what we want to happen, so to speak. So you are probably familiar with what's the probability of getting a 5 when you roll a die? Well, it's 1 in 6, okay? Well, in geometric probability, the probability is it's really talking about areas. So for geometric probability, the probability that it includes a geometric measure, so like length or area. So when thinking about areas and the probability that something will land in a certain spot of a geometric region, we're going to use sort of the following formula. We're going to be looking at finding the area of the shaded region, or really what we want to happen, where we want it to land. And we divide that by the total area where it could land. So it's the total area where it could land. So if we're looking at length of something, we're looking at what's the length of the part where we want it to land again, and compared to the length of the whole segment where it might land. So you can kind of think about this sort of in terms of carnival games. I think that's a really good way to sort of look at it. Now, this is a little bit lighter topic. So hopefully after working really hard on those last 3 lessons, I know these are tough. So this is a little bit lighter to start this out and to finish up with chapter 11. But we're going to be spending some days on some review and then testing towards the end of the week. So for example, it says, if you throw a dart at this shape, what is the probability that your dart lands in the shaded space? Well, this shaded space is right there. So how do we find that area? Well, to find the area of the shaded space, we have to find the area of the square and subtract the area of the circle. So the square is 10 by 10, so the area of the square is 100. We subtract the area of the circle. Well, some of you might be going, well, how do you find the radius or diameter? But remember, this is also 10 right here. So my radius is 5. So that means the area of my circle is pi times my radius squared. So when I take 100 minus pi times 5 squared, okay, that is the area of my shaded, okay? So this is my shaded, and I divide that by the total area. So what's the total area where it could land? Well, that's just the 10 by 10 square of 100. So if I take 100 and subtract 25 pi, that gives me 21.46, all divided by 100. So when we divide that, we would get 0.2146, or if we want to give as a percent, 21%. Actually, we could probably be a little bit more exact, but approximately 21%. Okay? So that's what we're really doing. If you're thinking about, you're playing a carnival game and you're throwing a dart, you want to win, okay? And you're going to win if you land in that shaded space. So let's take a look at a few other ones. So when I first started out and we talked about this sort of how you find geometric probability, we said the area of the shaded region, but you really have to, it depends on the problem, because in this next problem it says if you throw a dart at this shape, what is the probability that your dart lands in the non-shaded space? So now what we want to happen is we want to find the area of the non-shaded, because that's where we want to have it. That's where we want it to land to sort of win, and compare that to the area of the total area. So the non-shaded here is pretty easy. So 9 times 3, 27. And the total area where it could land is anywhere in here. So you get 9 times 15. And so when you calculate 27 divided by 135, that gives you 0.20 or 20%. And if you want to give as a fraction, remember the easiest way to turn your decimal back into a lowest terms fraction is just to go ahead and divide it, and then this is actually also 1/5. And then divide your fraction, you'll get a decimal, but then change your decimal back to your fraction using that math button. All right, so let's keep moving on here. Here's the length ones, and these really are not that difficult, but they seem to trip students up at the beginning. So it says, find the following probabilities of choosing a random point on AD. So if you're just like randomly, boom, choosing a point, randomly, boom, choosing a point on that whole segment from A to D, okay? What we want to do is we want to find the probability that it lands on this segment right here, this segment right here, BC. Well, how long is that segment? That's 5. What's the total length where it could land? Well, that's 6 plus 5 plus 3, or 14. So the probability is 5/14. And we can leave it like that, or we can divide it, or we can give it as a decimal or a percent. So now what's the probability that it lands on CD? Okay, see if I can get another color here. I'm not having much luck. Okay, there we go. All right, well, what's CD? CD right here. What's the probability that lands on CD? That would be 3/14. And the probability that lands on AC? Well, we're just going to have to, some colors are being finicky. All right, A to C is from here over to here. Thought I got a different color, but apparently not. So let's go with the highlighter here. So now we're looking at A to C, which would be 11/14. All right. Now, of course, they get a little trickier, and you got to, use some other strategies, and eventually going back to the shaded regions work that you did on that applications worksheet, that kind of applies here. That's what the work we did to kind of prep for this. So this one says, suppose the 3 circles on the target had radii of 4, 12, and 20. So what that means is that you have the smallest radius is 4, okay? You have this radius is 12, and then the radius all the way from the center, okay, all the way to the outside is 20, all right? So if you choose a random point on the target, what is the probability of hitting the red region? Well, so we want to find the area of the red, because that's where we want it to land, and divide that by the total area. Well, the area of the red is the radius of 4, so it's pi times 4 squared. The total area would be anywhere in this whole entire region. Okay, so that's the radius of the larger circle. So that would be pi times 20 squared. So again, just divide, and or you can calculate these separately, but you're really just going to divide and get probably your decimal. And if you want to change that again back to a percent, that would be 4%. So let's work on the second part of this. It says find the probability that it lands in the blue region. Okay, so I'm going to erase this highlight. Okay, so now the probability that it lands in the blue region, we have to find the area of the blue region. And then we have to divide that by the total, which we already know. Well, the area of the blue is going to be the area of the blue of the total circle minus the white circle. The white plus the red, really. So the total circle would be your 20 squared pi. I guess I'll write it in the correct order like I did above, just so it's not confusing. So our total area is pi times our 20 squared. Then we subtract the white and the red combined. So we're subtracting this right here, which would be a radius of 12. So now I have pi times 12 squared, and I divide all of that by pi, my total area, pi times 20 squared. And so if we take find the total of the area of the blue then is 804.25. I divide that by total area, which is 1,256.64. And so that gives me approximately 0.64 or 64%. Okay, let's try one more here. Yep, we have one more here, and this one's going to go back and might look similar to one of the shaded regions problems you did. But we're going to have to use some, either some trig or some 30, 60, 90, 45, 45, 90 relationships to find this. So let's just get started. So it says, if you throw a dart at this shape, what is the probability your dart lands in the shaded space? So what we're looking for is the probability of the shaded, okay? So our shaded space right here and here and here is going to be the area of the circle minus the area of the hexagon. So then I'm going to take that and I'm going to divide that by the total area, which is going to be just the area of the circle. So let's work on, well, the circle is easy because we have the radius at 7. So we have pi times 7 squared. And now we're going to work on the hexagon. We have to subtract that hexagon. Well, in order to find the area of that regular hexagon, okay, remember I have to take 1/2 the apothem times the perimeter. I don't have either one of those. So let's work on finding this apothem right here. Okay, so again, each one of these triangles in here, if I take 360 divided by 6, each one of those is 60 degrees. So this is 60. So that means this angle right in there is 30. So again, I'm going to come back out and draw this. We have 30. We have a right angle, and we know that this radii is 7 right there. And so I can actually find my apothem, okay, right here. And I'm going to actually be able to find this side, I'm going to call it x, using my 30, 60, 90 relationships. So remember, in your 30, 60, 90, you have this shorter side is x, your hypotenuse is 2x, and your longer side is x squared root of 3. So now we can take a look at that, and if the 7 is 2 times x, then x has to be 3.5. So this little piece right here is 3.5, so the whole side length right there is 7. So actually now we can get our perimeter by taking 7 times 6, or 42 there. Now let's work on the apothem. Well, if this is x is 3.5, then our apothem is x times the square root of 3, or 3.5 square root of 3. So now I found my apothem. Well, that's going to be that's a little messy. So I'm going to rewrite it over here. So I have 3.5 square root of 3, and then I still have to multiply that by 1/2. So now, once I calculate this, I have the area Oh boy. I'm not able to get another color here. There we go. So now, okay, I have the area of the shaded divided by the total area of the circle. And so if I multiply pi times 7 squared and subtract 1/2 times 3.5 square root of 3 times 7.6, again, just enter all of that in your calculator, and what you're getting then is 26.63 approximately, and then we divide by the total area, which is pi times 7 squared, which is approximately 153.94. So that gives us 0.173 or 17.3%. All right. You may want to read through the textbook and look through some additional examples. What I'm going to have you do for homework today, since this is a little bit lighter lesson and some of you are more comfortable with probability than others, I am just going to have you choose, okay? So you're going to decide, and I would like you to pick a minimum of 15 problems. You choose whatever 15 problems make sense to you, okay? Take advantage of my office hours, and I will be hosting another Zoom session probably on Tuesday, so you can look for that as we work on getting ready to review and test. Have a great day.